Hello, this is Tracy. We are going to discuss inference about two population proportions. We are going to determine the needed conditions to conduct our analysis. We are going to find a confidence interval for the difference between two population proportions. It's important in this section to perform hypothesis tests about two population proportions, but I won't be covering that in this particular PowerPoint. And we're going to interpret results in the context of the problem. Your Hawks Online homework is 12.3 and does include both confidence intervals and hypothesis testing. So, in order to perform our analyses, as always, you need random samples and a good study. Our sample proportions must come from two simple random samples. The two samples must be independent. You can't have paired samples. You can't have samples that are dependent upon each other. The samples, as we've seen in previous hypothesis testing, confidence intervals, normal estimation for the binomial distribution, samples must be large enough that you have at least 10 successes and 10 failures in both samples. Let's remember our notation. Remember P, at least in this, means the population proportion, which I know gets confusing because that letter P shows up in so many things. P is also the letter we use to represent a p-value. P is also the letter used to represent the probability of a success on an individual trial. Capital P means probability in general. But for right now, P is our population proportion, and we want to make sure that we are paying attention to the context. Do not get your population proportion, your sample proportion, mixed up with a p-value. So your population proportion is the number of successes in your population divided by your population size. P equals X over uppercase N. P hat is the sample proportion. That's the number of successes in your sample divided by your sample size. X over lowercase n. So if we have two groups, group 1 and group 2, each group is going to have its own sample size, it's going to have its own number of successes, and it's going to have its own sample proportion. P hat 1 is the number of successes in sample 1 divided by the size of sample 1. P hat 2, number of successes in sample 2 divided by the size of sample 2. Keep track of which group is group 1 and which group is group 2. When you're doing your hypothesis testing in the calculator, it doesn't matter as long as you keep track and you make sure that your greater than symbol or less than symbol matches. Make sure that you keep that straight. But when it comes to confidence intervals, you have to, unless you want to do some really fancy work after you run your calculator, you want to have group 1 picked so that in the wording, the difference between group 1 and group 2, group 1 is the group that comes first. Otherwise, you're going to have to do some crazy stuff once you get your confidence interval. And what does that word difference mean? The difference between 9 and 12. Well, that means 9 minus 12. And the order of those two numbers matters. The difference between 9 and 12 means 9 minus 12. You can't change the order or you're going to have your sign backwards. Find the difference between the proportion in the first group and the proportion in the second group. P1 minus P2. You have to keep your order straight, otherwise you're going to get your signs backwards. 9 minus 12 is a negative 3, and that's okay. It's okay to have a difference that's negative. It just means that 9 is smaller than 12, so when you subtract, you get a negative number. The difference between the proportion in the first group and the proportion in the second group, P1 minus P2, it's okay if that's negative. It just means P1 is smaller than P2. Make sure you keep things in the correct order. The difference between A and B, A minus B. All right. As you've probably noticed when dealing with proportions in our calculator asks us for x, a number of successes, and n, a sample size. That holds true when we're dealing with two proportions as well. X1, number of successes in group 1, sample 1. X2, number of successes in sample 2. N1, size of sample 1. N2, size of sample 2. However, sometimes the problem doesn't tell you the sample size and the number of successes. Instead, it tells you the sample size and the proportion or percentage of successes in each group. And in that case, to use our calculator to do our statistical testing for us, we're going to need to calculate the number of successes in each sample. So, 320 women are sampled, 40% prefer brand A above all other brands. 450 men are sampled, 35% prefer brand A above all other brands. What are X1 and 2? X2. What are the number of successes in group 1 and group 2? Well, we need to figure out what's group 1 and group 2. If this were a hypothesis test, doesn't matter. If this is a confidence interval, we want to be careful. Assume we are considering the difference between the proportion of men and women that prefer brand A. The difference between men and women. Men comes first. Men is group 1. Assume we are considering the difference between the proportion of men and women that prefer brand A. Men comes first. Men is group 1. X1 is the number of successes in group 1. X1 is the number of men who prefer brand A, because men is group 1. We are told 35% of men, 450 are sampled, let's say, 450 men are sampled and 35% prefer brand A. So 35% of 450 is the number of men who prefer brand A, the number of successes. So 35% is 35 over 100 is 0.35. 0.35 times 450 gives us 157.5 men who prefer brand A. No, our calculators will not accept that. You cannot have half a success, so you need to round that to the nearest whole number. Round up to 158 because 157.5, 0.5 or higher, round up. So X1 is 158. X2, the number of successes in group 2, is the number of women who prefer brand A. 40% of the 320 women sampled prefer brand A. 0.4 times 320, X2 is 128. If we are going to find a confidence interval for the difference between two population proportions, our Hawks Online homework likes to walk us through some steps. First step is find the point estimate. That's important to know. In our samples, what is the difference between the two proportions? What is the difference between the proportions for the two samples? We want to find that because we want to know it, but it's not something that we are going to use to build our confidence interval. I mean, you can if you want to. You can use the steps in the textbook and then the Hawks homework to build that confidence interval, but I'm going to talk about how to use your calculator to find the confidence interval. So we want the point estimate, but we don't need it if we're using our calculators in order to find the confidence interval. Hawks step 2 is find the margin of error. Again, we won't be using that to build our confidence interval. What we're going to do is use the calculator to build the confidence interval, and from that we can figure out the margin of error. So we want to find the whatever percent confidence interval for the difference between the proportion in group 1 and group 2. And we're going to use our calculators. Then we're going to interpret the confidence interval in the context of the problem. So here's the problem we're going to work. An article published in USA Today stated that in a study of 200 colorectal surgery patients, 104 were kept warm with blankets and IV fluids. 96 were kept cool. The results show only 6 of those warmed developed wound infection versus 18 who were kept cool. We want to find a 95% confidence interval for the difference between the proportion of patients who developed wound infection when kept cool and when warmed. We want to find a 95% confidence interval for the difference between cool and warm. Cool and warm. Cool comes first. Group 1 is going to be patients who were kept cool. So we want to find the point estimate. Again, we're not going to use this point estimate to construct the confidence interval. We'll use our TI, but we still want to know the point estimate. We're going to find a 95% confidence interval for the difference between the proportion of patients who developed wound infection when kept cool and when warmed. So we're going to find p hat 1 minus p hat 2. We use the sample data to find the point estimate for the population. Group 1 is the group that was kept cool because that comes first in the sentence about the difference between. And group 2 is the group that was kept warm. It's a lot of times easiest if you put this in a table and clearly label, and then you're less likely to make screwballing mistakes as you go. So, here's the table that we can use to help keep our data organized. Group 1 is the group that was kept cool. Group 2 is the group that was kept warm. We want x1 and n1 because we're going to enter that into our calculator, and we're going to use those to find p hat 1. So x1, the number of patients that developed wound infection of those who were kept cool, there were 18. N1, the number of patients who were kept cool in our study. 96 patients were kept cool. To find p hat 1, we take that number of successes in the sample divided by the sample size, 18 divided by 96. Bam, 0.1875. 18.75% of the group that was kept cool developed wound infection. Now we look at group 2. X2, the number of successes in group 2. Developing a wound infection doesn't sound very successful to me, but because that's what we're studying, that's what we call a success. 6 of the warm patients developed wound infection, and 104 of the patients were kept warm. X2 equals 6, and 2 equals 104. P hat 2 is 6 divided by 104. That is the estimate for the population. This is the sample proportion that developed wound infection when kept warm. It is the estimate for the population proportion, 0.05769. Only about 5.8%, less than 6% of the patients that were kept warm developed wound infection. If this is a statistically significant difference, and we have to do some analysis to figure out if it's statistically significant, but if this were a statistically significant difference, this is a practically significant difference as well. Over 3 times as many, 3 times the percentage of cooled patients developed infection as compared to those that were kept warm. Okay, so how much of a percentage difference is this? P hat 1 minus P hat 2. That's the difference between the proportion developing wound infection when kept cool and kept warm. 0.1875 minus 0.05769 is 0.1298. Our homework, I believe, only asks for 3 decimal places, so we would round that up. The 8 tells us to round the 9 up to a 10. 129 rounds up to 130. So 13%, 13 percentage point difference between the 2 groups. That's kind of a big deal. So margin of error. Yeah, it's step 2 in the Hawks homework. Let's find the TI's confidence interval and then backtrack to get the margin of error. So we need to find the 95% confidence interval first before the margin of error. 95% confidence interval for the difference between the proportion of patients who developed wound infection when kept cool and when warmed. So, use our calculator, the stats class, our favorite button on the calculator, stat. Confidence intervals and hypothesis tests are both types of tests. So arrow over to tests, and then you need to scroll down off your screen because we are comparing two proportions in a confidence interval. So we need two proportion Z interval, and that doesn't show up on our screen until we arrow down, down, down to letter B. Two proportion Z interval. Two population proportions, and we're looking at a confidence interval. And there on the left, you can see the screenshot of what your calculator will show you. And it's saying, hey, I want the number of successes and the sample size for group 1, the number of successes and the sample size for group 2, and the confidence level. And that confidence level is whatever confidence interval you're looking at. Here's where it comes in really handy to have that table with x1, x2, n1, n2 laid out for you, because you're literally going to copy right from your table into the calculator. So we do that, and ba-bam, here is our confidence interval. And look at that. P hat 1, 0.1875, just like we did before. P hat 2, well, that's a few more decimal places, but yeah, you get the idea. And it tells us what our N1 and N2 are, just so that we don't forget. We know that we set things up correctly. So those two numbers in parentheses, that's our confidence interval. Our confidence interval is the values between 0.0398978 and 0.21983. What this says is that we believe the difference in the proportions is somewhere between these two values. Now from this, we can go back and find the margin of error. Go back up to step 2. We can either take that point estimate for the difference that we got, remember that 0.1298, and subtract the lower bound, because that point estimate should be right in the middle of the confidence interval. Or we can take the upper bound minus our point estimate. And you see those calculations performed below. Now you notice when you subtract, you may not get exactly the same thing. That just has to do with rounding. You should get very close values, and Hawks, it gives a little leeway. So if you're a little bit off, it'll still take it. So either one of those is fine. You can go halfway in between, but there's your margin of error. 9 percentage points. All right, what on earth does this mean? Confidence intervals always mean the same thing. We are blah percent confident that the true whatever is within the two bounds for our confidence interval. We are 95% confident the difference in proportion of patients who get wound infections when kept cool and when kept warm is between 0.040 and 0.220. We round to 3 decimal places. That gives us the nearest tenth of a percent. We are 95% confident the difference between these two groups is between 4% and 22%. Now, it really does look like the proportion of patients who get wound infections when kept cool is bigger than the proportion of patients who get wound infections when kept warm. Because we believe, we're 95% confident, the true difference is between 4% and 22%. Bigger than 0, more than 0. So, more cooled patients get wound infections than warmed patients. If that confidence interval contained the number 0, we wouldn't be all that confident that the two groups really are different. If our confidence interval contains the number 0, then it's not ridiculous to think that there is a 0% difference between the two groups. Because our confidence interval does not contain 0, all the numbers are positive, we're pretty confident that the proportion of patients who get wound infections is indeed bigger than the proportion of patients. The proportion of patients who get wound infections when kept cool is bigger than the proportion of patients who get wound infections when kept warm. That's kind of important to know. We can also perform a hypothesis test, and it should give us similar results. All right, as always, if you have any questions, please let me know.